Air Cleaner Home Textiles to Reduce Indoor Air Pollution, a Preliminary Study. Abstract: indoor pollution sources that release gases or particles into the air are the primary cause of indoor air quality problems. Inadequate ventilation can increase indoor pollutant levels by not bringing in enough outdoor air to dilute emissions from indoor sources and by not carrying indoor air pollutants out of the area. High temperature and humidity levels can also increase concentrations of some pollutants. In this study, cotton fabric is treated with natural mineral, expressed as natural mineral 1, and exposed with carbon monoxide, carbon dioxide, nitrogen dioxide, and sulfur dioxide gases individually. After passing through the fabric samples, untreated and treated with mineral, these gases were analyzed quantitatively. Study indicated that there was a sharp reduction of these gases after passing through the mineral-treated fabric as compared to the untreated fabric. 1. Introduction to indoor air pollution. Indoor air quality, IAQ, has been of concern to scientists since long, but recent trends of IAQ in North India, especially in winters, is big matter to concern. It is recognized that exposure to air pollutants, found in the indoor environment, plays a significant role in human health. Generally, a human spends a significant proportion of his/her time indoors, 1,2. Some effects on health may show up shortly after a single exposure or repeated exposures to a pollutant. These include irritation of the eyes, nose, and throat, headaches, dizziness, and fatigue. Such immediate effects are usually short-term and treatable. Sometimes the treatment is simply eliminating the person's exposure to the source of the pollution, if it can be identified. Soon after exposure to some indoor air pollutants, CO, CO2, NO2, formaldehyde, etc., symptoms of some diseases such as asthma may show up, be aggravated or worsened. Exposure concentrations vary and depend on a number of factors including individuals' behavior and activities, pollutant sources, and geographical location, etc. The statistics suggest that the world's largest single environmental health risk, where 3.3 million deaths are blamed on indoor air pollution in contrast with 2.6 million deaths blamed on outdoor pollution in 2012. 3. In developing countries, health impacts of indoor air pollution far outweigh those of outdoor air pollution. Studies show that atmospheric pollutants concentrate indoors to high levels. Indoor concentrations are usually 2 to 5 times and sometimes 100 times higher than outside concentrations. 4. There are multiple and complex factors that affect the range and magnitude of indoor pollutants and associated health problems. Dampness is known as a major factor contributing to this, but the relationships are not fully understood. 5. Hazards induced by these pollutants vary, but can be summarized to exacerbating known respiratory diseases, sensitizing to airborne agents, and reducing lung functionality. A comprehensive Italian study on children, N equals 20,016, mean age equals 7 years, and adolescents, N equals 13,266, mean age equals 13 years, concludes that avoiding mold and dampness alone decreases the occurrence of related illnesses by 4 to 7%. 6. Of course, the actual case of exposure is to a wide array of different pollutants in situations where complex social factors are at play. 7. The industry in response has already introduced a wide range of air cleaning/treating products to the market, and the removal of both chemical and biological indoor contaminants. A plethora of devices have been designed to enhance indoor air quality through the use of filters, UV light, chemical or biological agents. Such devices can be energy intensive, contribute to some other form of contamination, and have a short operational life. It is possible that a passive solution can overcome such limitations. For example, home textile, which is widely used in every household around the world, such as curtains, bed sheets, sofa covers and carpets, etc. In the present study, effect of natural mineral treated cotton fabric in reduction of indoor pollutant gases is experimented. 2. Experimental. 2.1 Material. Natural mineral 1 was procured from the local supplier and cotton fabric with 250 GSM plain weave, 1 up 1 down, woven fabric was used in the study. 2.2 Methods. 2.2.1 Preparation of mineral dispersion. For this study 2%, 4%, 6%, 8%, and 10% natural mineral 1 dispersion were prepared using water as solvent. These dispersions were ultrasonicated for 20 minutes for stable dispersion. These various concentrations of mineral dispersion were further used to treat the cotton fabric. 2.2.2 Application of mineral on cotton fabric. The natural mineral 1 dispersion was applied onto the cotton fabric by using padding technique. The fabric was padded in prepared dispersion of natural mineral 1 and followed by NIP. 2 dip and 2 NIP was done for each fabric sample. These samples were dried at 600 C for 15 minutes. In this way 5 treated samples were prepared. These samples were investigated for pollution absorption capacity for 4 major gases responsible for indoor pollution. 2.2.3 Testing pollutant gases. To check the pollution absorption capability of treated fabric, a fabric toxicity tester was used. This tester consists of a smoke generation chamber. The smoke is generated by burning textile materials, and the gases, namely carbon monoxide, carbon dioxide, nitrogen dioxide, and sulfur dioxide, so liberated gases were analyzed using colorimetric detector tubes. These tubes can detect and quantify the concentration of these gases. Figure 1 shows the toxicity tester. In this study, a PVC-coated textile material was used to generate these pollutant gases. These gases were detected using colorimetric tubes placed in the narrow gas exit hole located on the chamber, as well as using air quality monitoring system. In the first part of the study, these gases were allowed to pass through the untreated cotton fabric, and then the concentration of these liberated gases was measured using air quality monitoring system. The concentration of these gases treated as blank. In the next study, instead of untreated fabric, mineral 1 treated fabric samples were used, and similarly the liberated gases were analyzed. Nitra. Figure 1, Toxicity Tester. 3 Result and discussion. All the 5 treated fabric samples along with 1 untreated fabric were exposed to various pollutant gases for different time periods to observe the effect of treatment on gaseous pollutants. After exposure for different time period of untreated and treated fabric with various gases, the concentrations of these gases were measured using colorimetric detector tubes and air quality monitoring system. The results of the gas absorbing capacity of the treated fabrics along with untreated fabric at different interval of time are shown in the figure 2 to 5. From the figures it is clear that untreated fabric allows to pass 10,000 ppm of CO2 gas, 50 ppm county gas, 15 ppm SO2 gas and 15 ppm NO2 gas. On the other hand, if the natural mineral 1 treated fabric samples are used, sharp reduction concentrations of these gases were observed. This study showed that natural mineral 1 helps in absorbing these gases. The earlier study has shown that this natural mineral 1 has very good CO2 absorption property, 8. Beside this, with the treatment of fabric with natural mineral 1, the porosity of the cotton fabric is reduced, which may also be additional cause of reduction of concentration of the gases. It was also noticed that with the increase of natural mineral 1 concentration on the fabric, the reduction of these gases improved. The time period for exposure of gases on the treated fabric also play an important role to reduce concentration of gas. This may be due to the further reduction of porosity of the treated fabric due to accumulation of gas particles on the treated fabric. For conclusions, the study indicated that application of mineral 1 on home textiles is one of the ways to reduce indoor pollutant gases. With the increase in concentration of natural mineral 1 in the solution, used for the treatment, the reduction of pollutant gases also improves. This may be due to the ability of natural mineral 1 to absorb these gases and reduction of porosity of the treated fabric compared to untreated fabric. Study also showed that if the exposure time is increased, the reduction of concentration of gases also improved. This may be due to the further reduction in porosity of the fabric due to accumulation of gas particles on the fabric. Acknowledgement. Authors are thankful to Ministry of Textiles, Government of India for sponsoring the project on development of air cleaner home textiles to reduce indoor air pollution.